Now, welcome to Magnetism lesson 15. We will have at the most 3 more small lessons to finish your magnetism completely. And what we will be dealing here with the magnetism of the Earth's magnetism called terrestrial magnetism. Now I will explain all these diagrams and each part of it very thoroughly. So first of all, have a look at these diagrams. This is a freely suspended bar magnet. This also I'll explain. This is a magnetic needle or a compass needle, and have a look at it, then I will explain. Now we already know a magnetic field is a vector quantity, and for a short bar magnet or a bar magnet, for a bar magnet like this, south, north, we had found out the magnetic field here on the axial line. We had found out the magnetic field here on the equatorial line. Here it was to this side, here it was to this side, right? And it is a vector quantity, so it has both magnitude and direction. And the magnetic field lines were like this. Means outside the magnet it is from north to south, and within the magnet it is from south to north. And in this video you have to have little imagination, or your 3-dimensional imagination. And all of you must have seen a compass. A compass, it is like a box, and at the center there is a magnetic needle, right? This is north pole of this magnetic needle, this is the south pole of this magnetic needle, and this needle is capable of rotating in the horizontal plane, right? Because the axis here is vertical. Now, if you tilt this compass like this, then the needle is capable of rotating in the vertical plane. If you keep it like this, the magnetic needle in the compass is capable of rotating, aligning itself. It is capable of rotating in a horizontal plane because the axis is vertical. If you keep it like this, then it is capable of rotating in a vertical plane. Now, let us come back. Why the Earth is a natural source of magnet? I will explain. Which exists everywhere near the Earth's surface. And on the surface, the value of the magnetic field is about 1 Gauss, that is 10 to the power minus Tesla. Actually, the exact cause of Earth's magnetic field is not yet known. It is believed the core of the Earth is still in the molten state, and the rotation of the Earth about its axis. The rotation of the Earth about its axis from west to east, that is 24 hours. It takes 24 hours to rotate once about the axis. Due to the rotation of the Earth about its axis causes the charged ions in the molten core. The charged ions to rotate because the Earth is rotating. Rotate along with it. And this, you can imagine, this is equivalent to the formation of a current loop, and a current loop behaves as a magnet, which produces the Earth's magnetic field. When the Earth is rotating about the axis, the charged ions present in the molten core also rotate with the Earth. It is equivalent to a current loop. That is probably the cause of the Earth's magnetic field. Now, what are the elements of the Earth's magnetic field? Elements, not does not mean chemistry elements, hydrogen, chlorine, fluorine, not like that. Now, B is a vector quantity. Magnetic field B is a vector quantity, means it has both magnitude and direction. So if you consider any point P, at any point P on the surface of the Earth, the Earth's magnetic field is characterized by these three quantities. One quantity is called magnetic declination. I will represent it by an angle theta. Then magnetic inclination, or called magnetic dip, that is delta. What is this? Supposing I will explain this in the next lesson. For the time being, what is this? If you hold a compass needle, if you hold a compass not horizontally like this, vertically like this, then the north pole of the needle or the south pole of the needle, depending on where you are on the surface of the Earth, will tilt from the horizontal position. The needle inside this compass, if you hold this compass vertically like this, means the needle is capable of rotating in a vertical plane, then either the north pole or the south pole will tilt like this, will tilt like this. Either the north pole will tilt down or the south pole will tilt down. The angle by which it tilts at a given place is called the magnetic inclination, or called magnetic dip. And I will explain you in the next video what will be its value. This is also an angle. What will be its value at different points. Then the horizontal component of the magnetic field. If these three things are known, then the magnetic field B, when the Earth is behaving as a magnet, natural magnet, is completely known in magnitude and direction. And these three quantities, they have different values at different places on the surface of the Earth. And if 1, 2, 3, these three are known, then B is known exactly in magnitude and direction at that particular place. Now let us analyze this figure. Now let me explain the Earth first. Now look, this is your Earth. This is your Earth, right? This gray portion, shaded gray portion, is your Earth. This is the axis. This is the axis of the Earth. And this side is east, this side is west, this side is north, this side is south. And your Earth is rotating about this axis, called the axis of rotation, from west to east, once in every 24 hours, right? Now, look at this. Look at this green. Look at this green circle. This is going all around the Earth. This is called your geographic equator. Geographic equator. Now, what happens if you suspend a bar magnet freely from a thread? This is a thread. This is a bar magnet suspended freely. Then this north pole of this bar magnet will not exactly point to this side, which is called north. This side is called east, west, north, south. Geographic east, west, north, south. East, west is a relative thing. Now, but this geographic north and this geographic south, they are fixed. This is a fixed point. This is a fixed point on the Earth. So this is the axis of rotation of the Earth. This is the axis of rotation of the Earth, and the Earth is rotating about this axis once every 24 hours. Now, if you suspend this bar magnet freely anywhere on the surface of the Earth, excepting this point and this point, I will tell you what is this point and what is this point. Now, then this bar magnet, this north pole of the bar magnet, actually does not point to this point north, geographic north. It points it aligns itself in such a way that the north pole of this freely suspended bar magnet points to this point on the surface of the earth, and this point from the geographic north is about, from here to here is about 400 kilometer towards the south. This point is to the south of this point, about 400 kilometers. It keeps changing also due to the variation of the Earth's magnetic field from time to time. So, the point on the surface of the Earth towards which this north pole of this freely suspended bar magnet points, that is this point, is called the magnetic north pole. This point is called the magnetic north pole. And the point just opposite to that is this point, is called the magnetic south pole. I will explain about these things. This is the horizontal component of Earth's magnetic field here. This is the vertical component of the Earth's magnetic field here. Now look. So, since the north pole of this freely suspended bar magnet is pointing to this side, and the south pole of this freely suspended bar magnet is pointing to this side, so this point is called the magnetic north pole. This point is called the magnetic south pole, right? So, why this north pole should point to this side? And why this south pole should point to this point? Means, when the earth is behaving as a magnet, which I just explained, because the ions inside the molten core are rotating with the earth, so it is behaving as a current loop, so it is behaving as a magnet. So when the earth is behaving as a natural magnet, then earth has a natural magnet, its south pole is here. Therefore, this north pole will be attracted to this point. And when the earth is behaving a natural magnet, its north pole is here. So, the south pole of this freely suspended magnet will be attracted by this, will be attracted to this north, right? So, now look, now this is a compass needle, this black portion, this is the north pole of the compass needle, this is the south pole of the compass needle. So when the earth is behaving as a magnet, which I have, it is not that there is a magnet inside the earth, I have drawn it here to explain it. Its south pole is here, its north pole is here. So the freely suspended magnet, the north pole of the freely suspended magnet will be attracted by this south pole, that is, it will point to this side, right? So, now look at, so therefore these are the magnetic field lines. These are the magnetic field lines. These are the magnetic field lines. They are not on the two sides, they are all around the earth. They are on the top, they are on the bottom, they are all around the earth. Now look, now the angle between this axis and this axis is 11.3 degree. So this green one I explained as your geographic equator, and this plane is perpendicular to this y-axis, and this is your Earth's magnetic axis, South pole, North pole. So the dipole moment of the Earth is directed from south to north, that is to this side. So all these magnetic lines of force are all around the Earth. And we know when a tangent is drawn to a line of force, we know if there is a line of force like this, what is the direction of the magnetic field here? Draw a tangent to it. What is the direction of the magnetic field here? Draw a tangent to it. A tangent to the magnetic line of force at a given point, either this or this, gives the direction of the magnetic field at that point that we studied in previous lessons. So here I have shown on one side, I have not shown on this side. So here if you draw a tangent, this is a tangent drawn to this line of force at this point. So here the magnetic field is this way. Now, so this is your B. Now, I will explain this part. Now, here a tangent drawn to this line of force at this point is pointing this way. So here the magnetic field is this way. Similarly here, the tangent drawn, this is the tangent drawn to this line of force. So the magnetic field is this way. Now, so this magnetic needle, if you keep at different places on the surface of the earth, how it will align itself. Now, how it will align itself. Look, before I explain that, let us look at this diagram. So this is your geographic equator. This is your magnetic equator. This is the surface of the earth. A person standing here. This point is same thing as this point. Right. And this point is same thing as this point. That is geographic south. This was your geographic north. A person standing here, his head will be to this side. A person standing here, his head will be to this side. A person standing here, his head will be to this side. A person standing here, his head will be to this side. A person standing here, his head will be to this side. Means we are, when we walk on the surface of the earth, when you consider earth's surface as horizontal, then we are walking vertically on it, right? Now, so here, if you hold a compass needle, the compass needle will be horizontal. Will be horizontal. Since it is horizontal, if something is horizontal, its vertical component is 0. Here, the magnetic field is pointing this way. That is parallel to the surface of the earth. That is horizontal. So that is why I have written, since it is horizontal, its vertical component is 0. And the horizontal component is not 0, right? That is what the meaning is. Now, if you take that compass needle to this point, and hold it like this, then your compass needle, this north pole will point vertically downward. At this point, the compass needle will stand. This compass needle will be vertical to the surface. This is your surface, the needle will be vertical. Since the needle is vertical, so the total magnetic field here is vertical, totally vertical. Here the horizontal component will be 0. Here BH means the horizontal component of the Mars magnetic field will be 0, and the vertical component is not equal to 0. So similarly on the other side, at this point, if you tilt your compass like this, means the compass needle is capable of rotating in a vertical plane, then at this point, the south pole. For the magnetic needle, the white portion represents the south pole, this dark portion represents the north pole. Similarly, if you stand here on the surface of the earth and you hold your compass needle vertically, compass like this, then the needle is capable of rotating in a vertical plane. Then the south pole, this compass needle, this is the south pole. The south pole will point towards this point, means the needle will be totally vertical. Since the needle is here totally vertical, therefore it has no horizontal component. So that is what I have said. So the horizontal component of the Earth's magnetic field here is 0, and it is totally vertical. The vertical is not 0. So at this point, At this point, that is the magnetic south pole, and this point, the magnetic north pole. Here the needle will be totally vertical. Here the magnetic needle, compass needle will be totally vertical. Means at these 2 points, at this point and at this point, the horizontal component is 0. The horizontal component is 0, and it is only vertical. Now, then at this point, not at this point, at this point and this point. In fact, I should not say at this point and this point. At all points around this magnetic equator, at all points on this magnetic equator which goes around the earth, where the magnetic field lines are horizontal to the surface, means at all these points, this point, all around the earth. If you hold a compass needle, the needle will be parallel to the surface of the earth. Means the total magnetic field at all those places, at all these places on the magnetic equator, since it is totally horizontal, so it doesn't have a vertical component, so the vertical component of the Earth's magnetic field at all points on the magnetic equator is 0, and it is only horizontal. Means it is not horizontal, is not 0, it has some value. So look at this one. This one is your geographic equator. I've just written equator. This one, the tilted one, this dotted one is your magnetic equator. These are the Earth's magnetic field lines. They are going all around the Earth. So what you have to remember is at this point, when you hold a magnetic needle, the north pole of the needle will point towards the earth. Means the needle will be totally perpendicular to the surface of the earth here. Means vertical. Means there is no horizontal component here. Similarly, at this point, the magnetic needle will be totally vertical, and the south pole will be pointing towards this point. So, since it is totally vertical, so there is no horizontal component. So, at this point and this point, the horizontal component, BH, horizontal component of the total Earth's magnetic field is 0. And at this point, the horizontal component of the Earth's magnetic field is 0. And it is only vertical, right? And at all points on the magnetic equator, this plane is perpendicular to this line at all points on the magnetic equator on the surface of the earth. When you draw a tangent to the line of force, that will give you the direction of the magnetic field, and since that tangent is parallel to the earth's surface at all these points, means it is horizontal, so there is no vertical component at all these points. That is, vertical component is 0, and it is only horizontal, Now that is all about. Now let me explain here. Suppose at some point the magnetic field is this way, and so if you split this magnetic field into two rectangular components, if this angle is theta, then this is your horizontal part and this is your vertical part. If theta is equal to 90 degree, if B is not to this side, is to this side, now this will be how much? BH will be B times cos theta, and BV will be B times sin theta. So if the magnetic field, this B, is pointing to this side, then theta is 90. If theta is 90, then cos 90 is 0. Cos 90 is 0. 0 into this thing is 0. Means horizontal component is 0. That is, here. Here the needle will be totally vertical. Here the needle will be totally vertical. Means magnetic field at this point and at this point, since the needle is pointing normal to the earth's surface at this point and this point, that is the magnetic field. Earth's magnetic field is totally vertical, means theta is 90, so the horizontal component cos 90 is 0, so the horizontal component is 0. So at this point and this point, the horizontal component is 0 because theta is 90 degree. And at all points on the surface of the earth on the magnetic equator, this B will be horizontal. This will be horizontal, means theta will be 0. If theta will be 0, then from here, at all points on the magnetic equator, the tangent to the lines of force will give you the direction of the field. Means theta is equal to 0. If theta is equal to 0, the B is not to this side, is to this side. So cos 0 is 1 into B is B. Means your horizontal component BH will be equal to B. And what about B sin theta? Since theta is 0, sin 0 is 0. So 0 into B is equal to 0, means BV will be 0. So at all points on the magnetic equator, BV is 0. BV is equal to 0. And at all other points, here, if you draw a tangent, means above this line, above this red line, at all points on the surface of the earth towards this side, if you draw tangent to the line of force, then this is your tangent, means this gives the direction of the field. This will be your horizontal component BH, and this will be your BV for all points on the surface of the earth above this line on the surface of the earth. At any point, if you draw a tangent, this is the tangent. So at this point, the magnetic field, the total magnetic field is this way. So this is the horizontal component BH, and this is your BV, vertical component. So what you have to remember, above this line, the vertical component of the Earth's magnetic field is pointing towards the earth, and the horizontal is horizontal. Similarly, all points below this red line, that is for all points on the surface of the earth, if you draw a tangent, the horizontal, here is your tangent. So this will be horizontal, and this will be your vertical. Means at this point, this is tangent. Means at this point, this is the direction of the magnetic field, total magnetic field. And this is your horizontal. This line is horizontal to the earth surface here. So this is your BH, and this is your BV. Means the vertical component of the earth's magnetic field, this is the horizontal component of the earth's magnetic field. Means for all points below this red line, the earth's vertical component of the earth's magnetic field is pointing away from the surface of the earth, and the horizontal is horizontal. And for all points above this red line, the vertical component of earth's magnetic is pointing inward towards the surface of the earth, and the horizontal is horizontal. So this is what you have to remember, these two concepts. This will help you to solve miracles. Below this red line means this is your magnetic equator. To this side of the magnetic equator, at any point on the magnetic field line, if you draw a tangent, that will give you the direction of the magnetic field. It will have two components, the vertical component and the horizontal component. So on this side, the vertical component of the Earth's magnetic field is pointing away from the surface of the Earth. This is your surface of the earth, away from the surface of the earth. And for all points here, above the magnetic equator, on the surface of the earth, the vertical component of the earth's magnetic field is pointing inward, right? So what is theta here? Let me explain you. Here this is theta, and here this angle is theta. Now the next two lessons will be very easy. So I think it is clear to you. So in the next lesson we'll study this magnetic declination, magnetic inclination, or called magnetic tilt in the horizontal component. What you have to remember, I tell you time and again, at which places the Earth's magnetic field is totally horizontal, that is at all points on the magnetic equator. It is totally horizontal. And at all those points, the vertical component of the Earth's magnetic field is 0. And at this point, that is the magnetic north pole, and this point as the magnetic south pole, the horizontal component is 0. The horizontal component is 0 and the field is only vertical. And at all other points, the magnetic field has two components, BH and BV. And below this red line, the vertical component of the Earth's magnetic field is pointing vertically outward from the surface of the Earth. And above this red line, towards this side, the vertical component is pointing towards the surface of the Earth, right? So that is what you have to remember, and we don't have much derivation in this chapter now. Now we'll go to the next lesson tomorrow.